As a final example of a symbol table client, we'll take a look at a mathematical application where we want to implement sparse vectors and matrices. So this is standard matrix vector multiplication that you learn in math, where we have a square matrix and a column vector, and we want to do a dot product of first row with the column vector to get the first entry in the result. So in this case, they're all 0 except for 0.04 times 0.9, which is 0.36. And then similarly, dot product of this with that column is 0.297, and so forth. So standard implementation of this is quite easy. We have a two-dimensional matrix, one-dimensional column vector for the multiplicand and the result. And then they get initialized in some way, but the main computation is a pair of nested for loops. For each row in the matrix, we have to go through each entry in the column vector and compute a running sum of, for that row in the matrix, the corresponding entry with the entry in the column, and add and keep the running sum, and then that's the result that we put in the result column vector for every value of I. And the key thing about this standard implementation, that it's two nested for loops that each run up to n, so that's n squared, or quadratic running time. And that's fine in typical applications when the matrix is small, or when there's lots of entries in the matrix. But the fact is that in many practical applications, the matrices are what's called sparse. Most of the entries are 0. And so symbol tables provide us with a way to provide a more efficient implementation of this process when we have lots of 0 entries. So in a typical thing, say maybe the matrix dimension would be 10,000, and maybe there'd only be 10 non-zero entries per row. Or even nowadays, you might have matrices that are even bigger, 10,000 by 10,000. If it was full, that'd be 100 million entries. So that's definitely going to be costly if you're doing this operation a lot. And the idea is to cut down on that cost by taking advantage of the idea that there's a lot of zeros. So let's start by just looking at vectors. The standard representation that we use for vector is to simply use a one-dimensional array. We have constant time access to every element, but the space is proportional to n. So even if there's a lot of zeros, we still have to take the space to store them all. Instead, we're going to use a symbol table representation where our key is the index and the value is the entry, and we just use that for every non-zero entry in the vector. So this has got the same amount of information. It says that index 1 has got 0.36, index 5 also has 0.36, index 14 has 0.18, and so forth. But the space is proportional, instead of to n, it's just proportional to the number of non-zero entries, which again in typical applications may be way, way less. And so now just we know we have a symbol table implementation that has efficient iterator, and also access is not bad. It's just that we're able to do it with way less space. So here's what the implementation of a sparse vector might look like. First thing is the representation is going to be a symbol table, and in this case we might as well use a hash table because the order in which we process things is not important. We just want to get at all the non-zero entries. The constructor is going to create in this symbol table, just a new symbol table that associates integer indices with double values. So the put, which is to store a value associated with an index I, is just put into that hash table, associate key I with value x, associate an integer with a double. and get, return 0 if the index key is not in the symbol table. We didn't, as the whole point was, we don't represent zeros. Otherwise, it returns the value associated with the index. And the iterable just returns all the key to iterate. And the most important thing is that if we want to do a dot product with a vector, say, then the time that it takes is only proportional to the number of non-zero keys. The 0 keys are going to be 0 in the dot product, so all we're going to do is take the ith entry of the vector and multiply it by whatever value we get for the non-zero entries. So it's a dot product that takes time proportional to the number of non-zero entries in the vector. And that's going to be important in the use of a matrix. So instead of using the standard matrix representation where every row of a matrix is an array, that's what a two-dimensional array is, and the space is proportional to n squared, now we're going to use a sparse matrix representation where each row of the matrix is a sparse vector. We can iterate through the elements in constant time, and with the hash table even get at them in near constant time. And then constant time in the average, but the space is only proportional to the number of non-zero elements, plus n for the extra symbol table overhead. So those are independent symbol table objects, but they allow us to have a much more efficient matrix multiplication method. So now, if we have a sparse matrix times a vector, our running time is going to be constant for each row, or proportional to the number of non-zero entries for each row, which means that the running time is going to be linear for a sparse matrix just by the use of a symbol table. And this clearly can make the difference between being able to address a huge problem. If we have a 10,000 by 10,000 matrix, we can get it done nearly instantly linear time versus 10,000 squared. If we don't run out of space, we might run out of time. But with the symbol table implementation, we can efficiently process huge sparse matrices.